Hello everyone, I'm Mohammad Rakif and I will be your instructor for this networking course. First of all, I would like to congratulate you for taking up this course. You made an excellent choice because this is the only course that will end your search. This course has several modules all dedicated to different topics in the networking world. So when you enroll, you will get to know everything from the start till the end. The curriculum starts with the very basic lectures of what are nodes, what are networks, how to set up those networks and much more. Then we dive deep into what are the addresses of the networks and also what are the different notations of those physical and logical addresses. You will learn everything about the topics related to the fundamentals of IT networking, and for the best part, at some of the important sections we are having a quiz at the end so you can recollect what you learned by answering those quizzes over the entire section. You will also learn how exactly the networking devices connect to the Wi-Fi using the 4-way handshake. That is a crucial step, and how do you use it in everyday life. So this is the right time to take action and get along with this course. So enough of the talk, let's get you started. I'll see you inside the course and thank you for choosing us. Alright, I would like to congratulate you again for the step you took. Now before starting, there are two things that I would like to tell you straight away. In some of the lectures where there is a need for you to visit a link or download something or some resources, you will hear me saying that the link is in the resources of this lecture or something similar. So when you hear me saying that the link is in the resources section or something similar, you have to go to the resources section attached to each individual lecture. From there, you can download the resources directly to your machine. And secondly, some of the videos in this course were recorded in the daytime while some were recorded in the midnight. So as a result, you might hear a variation in my voice across different sections of the course. But I assure you that as long as you are listening carefully to the topic, you will have no problems or no disturbances at all, and that is my guarantee. So those were the two important things, and without making you wait any further, let's start up with the first section of our course, that is the networking devices. Welcome to the section. Alright, we will start with understanding what is a network and why do we care for it. Going by the definition, a network is an interconnection between two or more nodes that share data. For now, we should not focus on the term nodes but on the definition itself. When two or more machines connect to each other so that they can transfer files, data or other information, they form a network. This is a simple put definition. To make transmission of data possible, we need a channel that can serve as a link between these two connected devices so that they can share data, resources and information over it. The connecting media or the channel can be of different types depending on the requirement of the communication. The nodes can be connected through a wired cable to form a wired network, or they can also be connected seamlessly without wires to form what we know as a wireless network. Now let us understand the concept with this analogy. This is a network of different people. So these are Shelly, Nick, Tommy, this is Laura, and then this one is Charles. So all of them have to share information, and so they decided to form a group or a network of their own so that they can share information on it. We all have networks of people we are connected to. In such a similar way, computers or nodes or devices come together to connect and make a network so that they can share the information across it. Such group of devices is also known as a computer network. So this is a computer network of 5 PCs, and all of them are connected together so that they can share data and information and also the resources through each other. So this is a computer network. Now let us talk about what I told you not to worry about, that is nodes. So what are nodes? In a computer network, nodes are the points or devices at which the communication either begins or stops. As you are listening to me, we are in a network. You and me are the endpoints, which is commonly known as nodes. I am the transmitting node while you are the receiving node because you are hearing me. In a nutshell, the nodes are the points in a network through which data flows or at which the data stops and starts. Like in our example, we only had 5 peoples. Let's go back to that. There are 5 peoples. That means this is a network of 5 nodes. In real networks, there can be thousands of nodes in a network or even more. So once again, nodes are the endpoints at which the data or information either starts or stops flowing inside the network. Now coming to an interesting point about the nodes. The nodes are called with different names on different types of networks. If you are using different types of networks, you might need to call your nodes with different names, and such is because of the following fact. If the nodes are connected in a wired network, they are referred to as hosts. If they are connected on a wireless network without the use of wires, they are called as stations. This is an important point and you should consider writing it down. If the nodes are using a wireless network, they are called stations, and if they use a wired connection, a wired network, they are known as hosts. So host on the wired one and stations on the wireless one. So in this example, we have 5 machines and all of them are nodes. The transmission of data follows through each one of them so that they can share the data across the network. So these are 5 nodes. On the left hand side, we have stations. Because they are connected wirelessly, they form a wireless network within the central laptop or central node. And on the right hand side, we have the host because they form a wired network, a wired connection between the central host and them. So the wired one are called host and the non-wired or wireless one are called stations. So these are some of the points about node, and you should consider the host and station ones in particular. In addition to the initiating and terminal nodes, there are also several other nodes that you should know about. Like we talked about how me and you are the terminal nodes because I am sending data and you are receiving data. Besides sender and the receiver, there are several intermediary nodes inside the network. These help in making sure that the data reaches from the sender to the receiver by falling through them. Such nodes are called as intermediary nodes. These subnodes help in establishing connections between both the ends for the transferring of data. Some of such common nodes are hubs, switches, routers, modems, etc. Also, the servers that you see on the cloud or physically, they are also intermediate devices between your laptop and the internet. Keep up everyone, we are going to start this section. By now you know about what are networks and what are nodes. And now you will learn the different ways you can connect these nodes together to form a network. Now let us dive in. The nodes in a network can be connected in any fashion as suitable for the environment. The orientation of nodes to form a network is termed as topology. In simple words, it shows in what manner the nodes are connected in a network. The topology shows in what manner you have connected the nodes to form a network. There are several topologies in a network formation as per the size of the network. So there are following types of network arrangement or topologies available for networks. These are the bus topology, ring topology, star topology, mesh topology, and hybrid topology. Now we are going to start with the bus topology, and from here on we will understand all of these topologies and their structures. Let us understand with the first topology of the day, that is the bus topology. The bus topology. In this type of connectivity, all the nodes are connected to a single main cable known as the backbone cable. So this right here, the orange one on which all the devices are connected, is the main cable, which is also known as the backbone cable. The backbone connects all the devices together inside the bus. Every node is directly connected to the backbone. This pattern somehow represents a bus and thus it is named so. Let us understand how this pattern works. Every node is directly connected to the backbone cable, and any message that needs to be transferred from the sender to the receiver is sent to the backbone cable. Since all the nodes are connected to the main cable, the message is received by all the nodes, irrespective whether they are the recipients of the message or not. This mechanism seemed fast, but it involves sending the message to the non-recipients of the message too, thus wasting a lot of bandwidth of the network. So now let us assume this laptop or the central node has to send the data to the printer, or you have to print something. So now if you send the data to the printer, the information will be sent to all of the devices, all of the 8 nodes present in this backbone. So the information is not just sent to the printer, it is sent to all of the devices that are connected in the bus topology. That is a huge wastage of bandwidth, and thus it is not encouraged. To recover from this, the concept of token came into action. Every node in the network is assigned a unique token number. For example, we have 8 nodes. Every node will have their own token number. For example, if we say we have token 1, 2, 3, 4 going from the left and token 5, 6, 7, 8 going from the right, we have 8 tokens for all the nodes inside the backbone cable or the bus topology. The message along with the token number is sent from the sender node to the receiver node. So in the case we discussed, if the laptop wants to send data to the printer, it will send along with the message 2 tokens, one the token of its own and second the token of the printer. Now when the message will go to all of the devices, they will see that we don't have the token of the printer, so they will discard the message and printer will have the same token number, and then it will accept the message and then print the data. So this is how the token works inside the bus topology. This solved a lot of time and the bandwidth of the network. The bus topology can be easily installed at low cost inside small offices or in places where limited or few devices needs to be joined. Bus topologies are often valued for their simplicity because less cabling is used and are lower cost of implementation. But this also comes with some downsides. So now let us look at the pros and cons of this network topology. The next one we have ring topology. So now we know that the nodes connected to a single cable forms a bus topology. But there is one more topology that involves a main cable or a backbone cable that we have seen right now. That is the ring topology. This is a topology where all the devices are connected to a single cable. Every node is connected to two other nodes on either side of the ring, on the left and the right hand side. The nodes form a closed ring when they are connected together, and thus they are named so. Like you see in the picture, the laptop is connected to the desktop on the left hand side and to the server on the right hand side. So each and every node is connected to two other nodes on either side of the ring, and thus they form a ring when they are enclosed inside a network. So this also uses a backbone cable because only single cable is used to connect all of them, but instead of giving it a shape like a bus, it forms a ring. Whenever someone has to send a message, it usually moves in one direction of the ring along the backbone cable. So if the laptop has to send information to the printer, it will flow unidirectionally. When there is only one direction to flow, it is termed as unidirectional ring network. Suppose this ring is unidirectional and the laptop wants to send data to the printer. Now going counterclockwise to follow one direction, it will pass through the desktop on the left hand side, through the server, and then reach to the printer. If the printer has to send a message in return, it cannot send back to the same path because it is unidirectional. Like it cannot send to the server and then to the desktop and then to the laptop along the same way. It will send the message to the backbone cable via the server on the right hand side and then back to the laptop, and it will pass through the other nodes as well. But with bidirectional ring networks, there is no such issue. Every node can send and receive data in both the ways or directions possible, either clockwise or counterclockwise. So if the laptop wants to send data to the printer, it can follow the path that takes the least amount of time to send the data to the receiver. In this section, we are going to talk about the different types of networks and the different types of connecting media that you can use to make such networks. So we will start with the types of network. Now comes the time to talk about the different kinds of network. All of the above explained topologies can be said to work together and form networks of different types. These networks can be categorized based on the architecture, network coverage area, or requirements of the nodes. The figure below shows the hierarchical order of different networks. So the smallest circle represents the PAN, PAN, or the personal area network. Now the bigger version of PAN is LAN, local area network. Now when you connect different LANs or increase the size of the LAN, it becomes MAN, metropolitan area network. And when different MANs gets connected together to form an even bigger network, it becomes WAN, or wide area network. Now let us understand in detail what these networks are and how these networks range or are different from one another. So the very first network we have PAN, or PAN. A personal area network, or PAN, is a small network with a coverage range of few feet or even more. These networks are not used for bulk data transfer, but they are ideal for connecting Wi-Fi or Bluetooth devices. We use such networks almost every day, just like for example, we have headphones connected to phones or headphones connected to laptops via Bluetooth, speakers connected to laptops via Bluetooth, and much more. The point to be noted is that The typical range of a PAN or a personal area network is around 10 meters, which is around 33 feet in total. To be able to be called connected to the network, you need to stay within 10 meters or 33 feet within the network. Below is a PAN which connects 5 devices together wirelessly. We have the phone in the middle, which is connected to the laptop. The phone connects to the headphones via the Bluetooth wirelessly. It sends data to the printer wirelessly via the Wi-Fi, and it also connects to the smartwatch at the right over here, and all of these works together within 10 meters or 33 feet. Now, excluding that this is a GPS smartwatch, I'm not talking about that. If this is a Bluetooth or Wi-Fi smartwatch connected to the phone, this watch needs to be within 10 meters or 33 feet of the range of the smartphone to be connected inside the PAN. The pros and cons of personal area networks are here. It is highly flexible, highly efficient for short network range because it works seamlessly wireless, and you will not see any lag because all of the devices are near the hotspot or what you call the server. It is easy to set up and relatively low cost. You set it almost every time, every day. It is easy portable. You can move your phone and your watch together. They are connected in a PAN and you can take them wherever you go. They are easily portable. They need less technical skills to use. Of course, even a small kid can make their own personal area network with their laptops, phones and Bluetooth headphones. So coming to the cons, we have low network coverage area or range. So this is a shortcoming of PAN. So as far as the range is concerned, if you go beyond 10 meters or 33 feet, you will suffer a network lag or breakage of connection or signals, and that is because they have low coverage area. Low data transfer rates, because these are small networks, the bandwidth of the network is not that good, so you have to keep in mind that the data transfer rates are low inside a PAN. Coming to the next one, we have LAN or local area network. A LAN or local area network is a small network, but it is bigger than PAN. It expands across multiple floors, offices, buildings, or even multiple localities. These networks are often used in offices, homes, schools, and libraries where different nodes are placed on different levels of the offices or in the schools or libraries or different sections of the libraries. A typical range of a LAN is around 100 to 1000 meters. So anything between 100 to 1000 meters is connected to a LAN. So we have talked about PAN, we have talked about LAN. Now moving towards the next one, that is MAN. MAN or Metropolitan Area Network is bigger than a LAN. It is just like LAN, but it is bigger and it expands across single or multiple cities, towns. So it is just like LAN, but instead of LANs, where LANs can cover different buildings, offices or localities, a MAN expands over multiple cities. A LAN cannot do that. A MAN expands over multiple towns. A LAN cannot do that. A MAN can. Now, there are no differences in how they work. The difference is on the range. So LAN is the local area network and MAN is the metropolitan area network, and all of the difference lies in the range of these networks. Multiple LANs are connected together to form a MAN. The next point will highlight that the multiple LANs are connected together to form a MAN. It is larger than a LAN in a single building, but not large enough to be considered a WAN or wide area network. For example, if you talk about what are MANs, in real life, MANs are usually networks such as dish TV or your cable operators, your telephone services, TV cable services. You are in one town, you are having those services. Your friend in another town is having the same services. That means that connection, that network is MAN or metropolitan area network that spans over different cities, different towns, even different localities. The range of a MAN is around 5 to 50 kilometers, while in the LAN it was around 100 to 1000 meters. So you can see the difference. Within 100 to 1000 meters it is LAN. In the 5 to 50 kilometers it is MAN or metropolitan area network. It is a much wider and bigger LAN. So the last one, or the wide area network, is the biggest possible network we have right now. A WAN or wide area network is bigger than MAN and it expands across the whole world. Not cities, not towns, continents. We are talking about continents and countries. So this is the biggest network that expands across the whole world. A WAN is essentially a network of networks, with the internet as the world's largest WAN. Since WANs are not tied to specific location, they allow localized networks to communicate with one another across great distances. So MANs and LANs are restricted because of geographical restrictions, but a WAN, which is the largest network, is not tied to such boundaries, and thus it connects the nodes from all over the world. Technically, any large network that spreads out over a wide geographical area is a WAN. The internet itself is considered a WAN, and the typical range of a WAN is around 100,000 kilometers or even more. So in the case of LAN, it was 100 to 1000 meters. In the case of MAN, metropolitan, it was 5 to 50 kilometers. And in the case of WAN, the largest network, it is 100,000 kilometers plus more. So anything beyond 100,000 kilometers and more is considered a WAN. Welcome to this section. We are going to talk about the networking devices inside any network and also how they work in the real life. So this is going to be an important section. There are lots of networking devices that contribute to make a network possible. So with the help of those devices, we can set up and establish a network. There are different types of networking devices that works on different layers of the OSI model. For now, you don't need to worry about what is an OSI model. We will learn about the OSI networking model in detail in the later sections of this course. Some of the networking devices we are going to discuss are the repeater, the bridge, the hub, the switch, the router, and most probably the multi-layer switch. So let's see what these devices are and how they work by using Cisco Packet Tracer simulation tool. So we will start with the repeater. A repeater is a simple networking device whose job is to repeat the signals inside the networks. So as the name suggests, the repeater repeats whatever signal is sent through it. This is a kind of retransmission of the signal or the data. So in the most simple terms, a repeater retransmits and boosts the signals from one device to the other device. The retransmission is useful in cases where the attenuation needs to be taken into consideration. And by attenuation, we mean the loss or degradation of the amplitude or the strength of the signals. While the message or the signal is on its way from the sender to the receiver or from the receiver to the sender, it gets attenuated. This attenuation or loss of energy can take place due to a leakage of signal from the cable, or from the climate change, or from the temperature, or from any radiation outside the environment. The repeater makes sure that the loss in this signal or the attenuation is covered up. This boosting of signal is beneficial for networks where the nodes are at larger distances from one another. But there is a limitation up to which a repeater can boost signals. A repeater, being only a two-port device, that means it has only two ports, it can repeat and boost signals only for two devices that are connected directly to it. So it is a two-port device, and that means there can only be two connections possible to the repeater. Another point to be noted is that it works on the physical layer or the first layer of the OSI model. Again, you don't have to worry about what is a physical layer and what is the OSI model. We will talk entirely about the OSI models in the later sections of this course. Till then, you just have to remember that a repeater is a two-port device that repeats the signals from one device to another, and it works on the physical layer or the layer 1. After the repeater, we have the hub. The hub is another networking device that helps in connecting the nodes together and forms a network. The main purpose of a hub is to make a network. An interesting thing about the hub is that it can do what exactly a repeater does. So just like a repeater, a hub can also repeat and boost the signals from the sender to the receiver and vice versa. Now the question you must ask is, if the hubs can do what a repeater does, then what is the difference between them? So you see, a repeater is only a two-port device. You cannot connect more than two devices directly to the repeater. For that, hubs have more than two ports, and thus they are a kind of multi-port repeaters. Besides repeating or retransmitting the signals, the hubs are also used to make networks by using their multiple ports. Several hubs can be joined together to form an even bigger network. So you can connect 5 or 6 devices to one hub, and you can connect the remaining network devices to another hub, and you can join those two hubs, and those devices will form an even bigger network. Just like repeaters, the hubs also work on the physical layer or the layer 1 of the OSI model. So you should remember that the hubs also work on the layer 1 or the physical layer of the OSI model. An interesting point to be noted about hub is that it is not an intelligent device. It always floods the channel in which it is associated. So even if you are sending a private message to anyone, the message will be flooded across every device that is connected to the hub. There are two types of hubs depending on how they work with the supply of energy: active hubs and passive hubs. The first one is the active hub, and these hubs operates on a power supply. These types of hubs need a supply of electricity to work because they amplify or boost the signals, which requires external energy. These hubs can regenerate a bad signal as well as amplify an attenuated signal too. While passive hubs, on the other hand, do not need external electricity to work. These hubs simply connect to the devices and they do nothing else. They neither regenerate the signals nor amplify them. They just pass the incoming signal from the sender to the receiver as it is. The next device we have is a networking switch. So a networking switch is a multi-port device that is used to connect different networks together. So remember, it is used to connect or make different networks. A switch is generally used for creating sub-networks within a main network. And also, just like what a bridge does, the switch can connect networks only and only if the subnets are same. So it cannot connect devices of the different subnets. A switch can try to connect different subnets together. It can try, but they won't be able to communicate with each other. And the reason for that is, even if the switch is successful in setting up a connection between the different subnets, they won't be able to communicate because the routing functionality is needed, which is provided by the router. So the switch cannot do the communication across different subnets alone. It needs the help of a router. Router is another networking device which we are going to talk next. There is much more what a switch can do besides making a network. For understanding that, you need to know what are subnets and how they work, what are VLANs, also the concept of collision domains, broadcast domains, and subnetting. If I start explaining these topics right now, some of you might get it while some of you may not. So it will be better to explain more about what switches can do and what is this collision domain, broadcast domain, VLANs in the later section of the course. For now, the work of a switch is to create networks by joining nodes together, and only if the subnets are same, they can be connected together and communicate to each other. Switches can be of multiple number of ports depending on how many devices they need to connect. They can have 18 ports, 12 ports, 16 ports, or even 24 ports. All of those ports can be used to connect separate networks to each other. Switches generally work on the data link layer or the layer 2 of the OSI model, just like a bridge. But there is a special type of switch that is known as a layer 3 switch or a multi-layer switch that works on the network layer or the layer 3 of the OSI model. So in simple words, you can say that a layer 3 switch is a combination of a router as well as a normal switch. Just like a bridge, the switch also stores the addresses of the node in its MAC address table known as MAC. But instead of storing it in its software like what the bridges do, a switch stores the address in its hardware. So the bridges stores the MAC addresses in the software while the switches store the MAC addresses inside its hardware. So now let's see how a switch actually works in the packet tracer. So we are going to discuss logical and physical network addresses. So a logical address are set logical because of the fact that they can change their value depending on where they are located inside a network. Such is because these are temporary addresses that are assigned by the network or the DHCP in particular. We will talk about DHCP in the coming lectures for sure. When these networks or DHCP servers change, the logical address of a node also changes. So for example, let's say if a node connected to a network A moves to another network, a network B, its logical address will change according to the address of the new network B. The same is true for the DHCP server. If a node is connected to a DHCP server A and it goes to another network and it gets connected to a DHCP server B, then its logical address will change according to the DHCP server B. So if you are sitting in an office, your current address is the office itself. But when you are at home, your current address changes to your home accordingly. Such is the concept of a logical address. The same is true for networks too. Such a logical address is named as an IP address or Internet Protocol address. Now, the problem is, since these logical addresses keep on changing depending on the location of the node, how a node can distinguish if it is talking to the new node which has came into the network just now or to the old node that was in the same network. Coming to an example, your temporary address was your office or either your home. Your address keeps on changing while you are traveling. So if you are going to the coffee shop, your local address will be the coffee shop, not your home. So if you travel a lot, your current address or the logical address will keeps on changing. And if such is the case, then how can a person find you when he needs you the most? For that, he or she needs your permanent address, which is your home. Similarly for nodes, since the logical address keeps on changing, there is another permanent address that helps in identifying a node uniquely. This address is known as a MAC address or Media Access Control address. This address is a permanent one and it never changes, just like the address of your home. In the figure, we can see a network of nodes with the logical and physical addresses as follows. The addresses in the green ones are the logical addresses, those are the IP addresses, and the addresses shown in the red are the physical address or the MAC addresses. So 10.0.0.1, 10.0.0.2, 3, 4, 5, these are IP addresses. These will keep on changing if all of the devices keeps on changing the network. Now the ones which are red are the physical address or the MAC addresses and they never change. Now let's quickly recap what we have learned in the previous lecture. We learned about two types of addresses, that are physical addresses and logical addresses. So the logical address are commonly known as the IP addresses, and we are going to talk about IP addresses in detail in this section. So an IP address or Internet Protocol address is a network address used for recognizing nodes or devices and also send the information between them. This address stores the information about the location of the nodes in the network. It tells us where in the network a particular node is located. So for example, if you are trying to locate any node, any device on a network, you need a logical address or an IP address of that node so that you can reach or you can drop to that location of the node in the network. The INA issues these addresses every time a node connects or requests an address from the DHCP service. Now let's say you have brought home a new laptop. Now you are opening it for the very first time and you have not configured it at all. For the very first time you are opening it, your laptop will connect to the DHCP server and it will request for an IP address or a logical address. That time the DHCP server issues an IP address to your network so that it can connect to the internet. That address is known as an IP address. An IP address consists of a combination of alphanumerals which are separated by dots or period. An example of an IP address will be like 192.168.14.32, and now in between those numbers there is dot separating them. So 192.168.14.32. There are 4 columns in this IP address, each representing 2 different parts of the network. We will surely talk about what these 2 different parts are in the later sections when we will talk about network portions and subnets and the subnet masking. But for now, you just need to remember that there are 2 parts in the IP address, that is the host portion and the other one is the network portion. There are 2 types of IP addresses we need to know about. These are IPv4 addresses and IPv6. That means IP version 4, that is the older one, and IP version 6, that is the latest one. An IPv4 or Internet Protocol version 4 address is 32 bits long. That means in that IPv4 address there are 32 binary digits that represents 32 bits of an IPv4 address. Since there are 32 bits in total, an IPv4 address range can accommodate 2 to the power 32 addresses. That means huge. In simple words, if you start the first node with the address 1, for example, let's say my machine has an address of 1, then the last node in the IPv4 address range will be 4.294.967.296, and it is huge. But in reality, even this massive address space that I'm not able to count falls short because of ever increasing number of new nodes joining the internet every day. An example of an IPv4 address is again 192.128.31.12, each separated by dots. Each such part is known as an octet because it contains 8 bits or 8 binary digits. So 4 times 8 is 32 bits in total. So 192 is 8 bits, 128 8 bits, 31 8 bits, 12 8 bits, 8 plus 8 plus 8 plus 8, that is 32. So this is 32-bit long IPv4 address. Similarly, an IPv6 or Internet Protocol version 6 address is 128 bits long in spite of 32-bit in IPv4. That means the combination of alphanumerals in an IPv6 address can be of 128 characters in length. Since there are 128 bits in IPv6, so 2 to the power of 128 bits is something that I am afraid of telling, and you can see it right on the screen. But we can be assured that there are so many addresses in the IPv6 address space that we will never be out of addresses in the near future. Note that an IPv6 address is separated by colon while the IPv4 by dot. So this is 2005:0db8. Now this is hexadecimal notation, and we will talk about why we need hexadecimal notation and why not binary notation for this. Now let's see how an IP address can be divided into different parts or bytes with this diagram. So in this diagram we have 192.128.31.12. So this is an IPv4 address. This is 32 bits. Now let's see what each part says. So if we dissect in 4 parts, we have 192, 128, 31 and 12, 4 parts. Now 192 in binary goes to 11 and 6 zeros. 128 in binary goes to 1 and all zeros. 31 goes to 000 and then all ones. And then lastly 12 goes to 0000, 11 and 00. So these are the representation of binary digits of 192, 128, 31 and 12. Each and every bit of these 4 blocks, so this is 8 bits, that is 11 and rest zeros are 8 bits, 1 and rest zeros are 8 bits, and then all of those 8 bits are 8 plus 8 plus 8 plus 8, that means 32 bits. So now you see every IPv4 address is made up of 4 columns or 4 sections, and each section within contains 8 bits or 8 binary digits, thus equaling to 32 bits in total. Now according to the definition of 1 byte, 8 bits equals to 1 byte. That means 8 bits collaborate to make 1 byte. So it will be nice to say that we have an IPv4 address of 32 bits, or rather we can say we have an IPv4 of 4 bytes. That means 4 times 8, that is 32. It's the same thing, 32 bits or 4 bytes, it's all your choice. So we have IPv4 address of 32 bits or 4 bytes. A MAC address or media access control address are the physical addresses of any device. They never change except by forcing them to. A MAC address is of 48 bits. That means there are 6 octets and thus 6 bytes in total. These addresses are permanent to a machine or a device, and they are used to distinguish a device on different networks. Like in our example of logical and physical address, in which we talked about you, your home and your office, an IP address is your current address which keeps on changing while you are traveling, while the MAC address is your address of the home that never changes and it is permanent for you. The MAC addresses can be split up into 2 major parts, which are the OUI part and the NIC part. Let's see what are those. The OUI, or the Organization Unique Identifier, is a part of the address that is unique to the network card. So a network card is inside your device, inside your laptop or computer, through which you can access the internet and everything. This is a 24-bit number that identifies the manufacturer, organization or any vendor, for example like Intel, Samsung, Cisco, Dell or any other organization. So in simple, the OUI, or the Organization Unique Identifier part, tells you what organization or which manufacturer has produced the network card inside your device. It can be an Intel's, a Samsung's, a Cisco or Dell's, or any other vendors that are publicly available for the network cards. The second part is the network interface part, or the NIC. This represents the serial number that is assigned to the adapter or the network card by the manufacturer. So you see The OUI identifies who is the manufacturer or who is the organization that made that card. And the second part, NIC, tells you what is the sequence number or what is the identifying number on that card. So NIC represents the serial number that is assigned to your network card. Since MAC addresses are permanent addresses for a node, they can never be same for two nodes ideally. Unlike IP addresses, which are represented in binary notation, so we talked about how IP addresses are defined by 0 and 1, those are the binary digits or the binary bits. MAC addresses are represented in hexadecimal notation. Now let's see why is that. This is due to the fact that MAC addresses are 48-bit numbers and they are very long to remember. So if you represent it in binary digits 0 or 1, it will be a very long number that will be very hard to remember. Let us understand the format of a MAC address with this diagram. So in this diagram, we have a 48-bit MAC address, that is 001A, 73C8, D7 and FD. So these are not binary digits, these are hexadecimal representation. So 00 will be in hexadecimal, 1A is in hexadecimal. Notice you can see the letters are coming up which were not in binary, so these are hexadecimal notations. We have 6 parts, so we have 001A, 73C8, D7, FD. Now let's try to calculate how many bits are there inside the MAC address. The first part, or the 00, can be represented in binary by 0000, that is the first 0, and the second 0 is 0000. So double zeros in hexadecimal represents to 8 zeros in binary. The next part is 1A. 1 can be represented in binary by 0001, and A can be represented in binary by 1010. You can refer to this table on the right hand side. This is a mapping of decimal to binary and binary to hexadecimal. The A, hexadecimal A, represents to 1010 in binary and 10 in decimal. So A means 1010, and that is why 1A means 0001, 1010. Similarly, the last part, that is the FD, in the table you can see F represents to all ones, so 1111, and D represents 1101. So FD represents to 4 ones, 1101. So now after decomposition, if you club all of the binary digits, all of the binary bits, it comes out that we have 8 bits, 8 bits, 8 bits. We have 6 times 8 bits, that is 48 bits or 6 bytes. So as I was saying, MAC addresses are written in hexadecimal. Now you can see the point why is such that, because in the last row you can see that instead of remembering 48 binary digits, you can remember 2, 4, 6, 8 and 12. So 12 hexadecimal digits instead of 48 digits. It's very much simpler to remember 12 instead of 48. So that is why hexadecimal is used for MAC addresses. Why cannot we keep the MAC addresses simple in binary format? Why we bother with this hexadecimal notation with this C, D, F, E's, 15s, etc.? So the answer for this is simple. In hexadecimal, we have the less number of bits corresponding to more number of bits in binary. So 1A in hexadecimal is represented as 0001, 1010 in binary. That means 2 bits in hexadecimal equals to 8 bits in binary. Similarly, 73 in hexadecimal is 0111 0011. 73 is this 8 bits. C8 is 1100 1000, and similarly all of those FD and D7 bits. In hexadecimal to decimal, we have 1A that is corresponding to 26 in decimal, 73 that corresponds to 115 in decimal. And by the way, I'm able to do this directly because first I'm converting this hexadecimal 73 into binary, and then from binary I'm calculating this decimal. Now looking at these figures, honestly tell me which one among these is easier to remember and has the least number of digits that you have to cram up for your MAC address. So out of these binary, decimal and hexadecimal notation, the best notation that was allotted to MAC addresses is the hexadecimal notation because of its shortness and ability to represent in less numbers. So MAC addresses are always in hexadecimals. By this, we came to the end of this section where you learned what are the network addresses, what are the roles and their types, how they change depending on the location, what are the IP addresses, what are the MAC addresses, and how to configure them, and lots of things. So the protocols we discussed, these protocols are stacked in such a way that it forms a model. So in the networking world, this protocol works on layers, and thus these layers forms a model. So we discussed some of the protocols and what they do briefly. Now the question arises is that how can so many protocols work together under one roof? The solution to this was to arrange them in an order such that all of them can work in conjugation with each other. This arrangement gave us a model which is popularly known as the OSI model, or the Open Systems Interconnection Model. The OSI model, or the Open Systems Interconnection Model, is a multi-layer network model that stacks the protocols on individual layers as suited. So that means on every layer of the model, that are the 7 layers, each layer will have some protocols, and some protocols will be working on those independent layers, and thus 7 layers will have different protocols working on each of them. This model consists of 7 layers stacked upon each other. The flow of data from the lowest level of physical bits to the highest level of application visualization is handled by these layers. So everything from the physical bits to the data that is understood by the application, everything is handled by these layers. As the data starts moving from the lower layers to the upper layers, each layer adds some new things that must be followed by the data at the individual levels. Now let us see what these 7 layers of the OSI model are and how the model is structured with all of them stacked upon. The figure shows the OSI model with 7 layers. So you can see here is the 7-layer OSI model, and the model starts from the bottom layer, that is the physical layer or layer 1. So the first one is the layer 1, that is known as the physical layer. This is the lowest layer of the model upon which other layers are stacked. Then we have the data link layer or the layer 2. So above that we have the data link layer. This layer handles all the layer 2 protocols and services like MAC addresses, and most importantly the flow control of the data. The third one is the network layer or the layer 3. This layer handles the means or the ways by which the message can be transported from one device to the other device. The next layer or the layer above that is the fourth layer or the transport layer. This layer handles how the messages will be sent and what will be the best way or the best option of doing so. As the name suggests, the transport layer is responsible for the transportation of messages from one node to other node. The fifth layer is the session layer. As the name suggests, this layer makes sure that before the actual transmission of data happens, the link or session is ensured between the two communicating devices. So the session layer makes sure that before the actual transmission takes place, there is a link through which the communication can happen. That is the purpose of session layer. The next layer is the presentation layer or the layer 6. This layer maps the application language to the computer language and vice versa. This means there is a language that is understood by the application, and then there is a language that is understood by the computers. Both of them are different, and the work of presentation layer is to create a mapping between two different languages. So it forms a mapping between different application languages and the standard computer language. The last layer or the top layer is the layer 7 or the application layer. All the application works and use this layer directly. So any application, any software, any website you are using, the application layer is directly in contact with that. This layer is something that the applications can understand. This layer also serves as a link between the user that is using the application and the layer that is beneath that is the presentation layer. So these are all the 7 layers of the OSI model, starting from the physical, the data link, the network layer, the transport layer, session layer, presentation layer, and lastly the application layer. Now this is very simple, but the sequence in which all these layers are numbered is very important, so you should note that down. So now we are going to talk about the upper layers of the OSI model. So there are 3 layers that contributes to the upper layer of the OSI model, and those are the application layer, the presentation layer, and the session layer. So we are going from top to down. So application was the 7th layer that was on the top, the presentation layer below that, and the session layer below the presentation one. So we have these 3 layers that are known as the upper layers. So let's see what each of them are. The application layer or the layer 7 handles all the protocols and services that are used by the applications on the internet or any network. Everything from HTTP sessions to DHCP and DNS services are handled by this layer. In simple terms, this layer interacts with the software applications that you are using or that any computer is using and make them work properly. All the communication that is happening using the applications is handled by this layer, and thus it is named so. So everything that your application needs, this is provided by the application layer or the layer 7. The next one we have the presentation layer. The layer beneath the application layer is the presentation layer or the layer 6. This layer converts the data format that is used by the applications. So the applications you are using, for example, an application Facebook. So Facebook might be using its own language and that cannot be understood by the computer. So the role of presentation layer that is below the application layer is to make sure that the language which the Facebook is using is to be converted into a language that the computer can understand. So in simple terms, this layer translates the syntax or the language that is used by the application layer to the one that the layers beneath that can understand or the computer can understand. So converting from a language that Facebook understands to a language that a computer understands is the work of presentation layer. For example, let's say that the application layer is talking in the language X. So let's say that the Facebook is talking in a language X, which is understood only by the Facebook as well as the user. Since the computer understands another language that is Y, which is not the Facebook's language, so the presentation layer converts the language X to the language Y so that the language Y can be understood by the computer. So this layer translates the data format used by the application to a data format that is used by the computer. So this is the work of the presentation layer or the layer 6. The next layer we have is the session layer. The session layer or the layer 5 is used for making a link that is known as a channel between the two communicating devices. So the main role of this is that it establishes a session or a connection between two communicating devices. Since before sending the messages, a communication channel or a link is necessary, and that is obvious because if you need to transfer something, you need a medium for that. So the role of this layer is to make sure that there exists a channel between the two communicating devices. So when the nodes are ready to transfer data to each other, this layer opens a session or a channel so that the communication can start. When the communication is actually happening, everything is managed by this session layer, and when the communication ends, it also terminates the session or the channel once the messages are being delivered and nothing else is to be exchanged. So the role of session layer is easy. It makes a session so that the messages can flow through it. It maintains that channel, and once the communication ends, it terminates the channel or the session. That is the working of session layer. So these are the top layers of the OSI model. Those are the application layer, the presentation layer, and the session layer. Now you need to remember what are the numbers of these layers because it gets very confusing. So application is layer 7, presentation is layer 6, and session is layer 5. So we are going from 7 to 1. The next layer is considered the heart of the OSI model because of its importance, and that is the transport layer. So let's see what does the transport layer do. Once the messages as well as the channel are ready, the messages are sent through the channel. The transportation facility is provided by the layer 4 or the transport layer. So everything related to transportation of data from one node to the other node through a channel is handled by this layer. Besides the transportation, flow control of the data, the sequence of sending the messages, the sequence of receiving the messages, the addresses of the devices that are communicating, and a lot of information is handled and added by this layer. So you can say this is the most hard-working layer of the OSI model. In addition to these, defining the port numbers on which port numbers the applications are communicating, the data transmission protocols, the TCP or the UDP according to the packets, the segmentation and desegmentation of data packets on the receiver side is also handled by this layer. In short, everything related to where and how the messages will go is handled by this layer. The next layer we have is the network layer. So let's see what is the network layer. This layer is the third layer of the model, and by the way, transport layer is the layer 4. The network layer or the layer 3 of the model sits below the transport layer. This layer provides the information about the data packets that are transmitted by the transport layer. So the transport layer transports the data from one device to other device. So every information about that packet is contained in the network layer. Since the transport layer needs to know the address of the devices that are communicating, this network layer comes into play. This layer adds the IP address of the sender as well as the IP address of the receiver so that the messages can go from correct sender IP address to the correct receiver IP address. The IP address is added on this layer or the layer 3, and thus another name for IP address is the layer 3 address. So you see, since the IP address is added on the network layer or the layer 3, IP address got its other name, that is the layer 3 address from here. So this is the concept. The IP address got its other name, that is the layer 3 address. The MAC address is a layer 2 address, and we are going to see why is that. Every information about the data packets such as the routing, switching, the use of gateways, subnetting, and everything that's related to the networking of those packets is handled by this layer. So in short, this layer focuses on sending the data packets to the desired devices using their IP addresses. The next layer is the data link layer or the layer 2 address. This layer adds another address to the data packet or the data frame that is known as the MAC address. So now you can see why the MAC address got its other name as the layer 2 address, because the MAC addresses works on the layer 2 or the data link layer. So in data link layer, the frames are added with the layer 2 address, which are known as the MAC address, and then it is sent to the upper layer, which is the network layer. Besides MAC addresses, additional information like flow control, error checks, and frame encapsulation are also done in this layer. Now besides these services, there is one point that you should note. There is a difference between what a message is termed in the layer 3 and what the message is termed in a layer 2. So in the layer 3, I am saying data packets, and data packets. But in layer 2, I am saying data frames. Remember this point. The messages, when they are working on the layer 3 or when they are held by the layer 3, those messages or those pouches of data are known as the data packets. While when these packets go to the layer 2 or they come to layer 2, these packets are termed as data frames, because data link layer works in frames instead of packets. So everything inside data link layer is seen as a frame. Therefore, every packet in this is termed as a frame. The last layer is the physical layer or the layer 1. The physical layer is the lowest layer of the OSI model, and its role is to convert the frames that are coming from the transport layer into the binary digits or bits so that the messages can be transferred in the form of signals from one device to the other device. So in simple terms, the role of the physical layer is to convert the data frames of layer 2 that is coming from the data link layer into data signals so that they can be transferred over the communication channel such as an Ethernet cable or a Wi-Fi signals, etc. Besides this, this layer takes care of what is known as the layout of the communication pins. In addition, other services of this layer includes the voltages, cable characteristics, what are the characteristics of the wire you are using, the frequency on which the messages are to be sent and received, etc. This layer also takes care of the transmission mode, such as using a duplex or a half duplex or a simplex channel modes. So in short, this layer focuses on the actual transmission of data in the form of signals from one node to the other node using a physical medium. Now let us understand how the various layers of the OSI model interact with one another by using a real-world application. So in this example, we are assuming that both the sender and the receiver are sending messages using the Facebook Messenger. That is an application. So we are assuming that the Facebook Messenger is operating on both the sender and the receiver's devices. So suppose the sender is sending a Facebook message to the receiver. So it will type something like, "Hello Muhammad." So let's say this is the message. So it has been typed in the Facebook Messenger. So you have sent me a message through an application, that is Facebook Messenger, using the application layer, and that message will come to my application layer via the same route. So this message goes to the presentation layer so that it can be transformed into another format. Now the job of the presentation layer is to convert that application message into a format that's understood by the computer. So the message that was hello Muhammad, that was sent by the Facebook Messenger, is now converted into binary digits or ASCII codes. So these binary digits and ASCII codes are a format that the computer understands. So these messages are converted to ASCII codes or binary digits by the presentation layer. This converted data is now ready to be transported to the below layer, that is the session layer. Now before sending the message to the lower layers, the session layer makes sure that there is a channel or a communication link that exists between the sender and the receiver. So this layer or the session layer connects the two devices by making a channel, a connection, a link or a session, whatever you call that. It makes a session or a link between the two communicating devices. So it forms a tunnel. You can see the tunnel up on the Facebook on the left and the Facebook on the right. So it is making a tunnel between the two devices or between the two applications that are running on either side of the communication. So whenever there is no need of communication to take place, this session is terminated and closed. So after the channel is created between the sender and the receiver, the ASCII code or the data that was converted by the presentation layer comes down to the transport layer, so that here in the transport layer it can be sought out how to transport that data. So when the data comes to the transport layer adds the port numbers that the machine or the application is using. Suppose the Facebook is using the port number 50, suppose. So the port 50 will be added to the ASCII code or the message. So this is a message, though the dark green one is a message or a packet. So it will be added inside the packet. So the data is sent from the sender's port 50. So in other words, it will be seen as like the sender's port 50 is sending a message to receiver's port 50, and port 50 is being occupied by the Facebook in our example. So the main thing is this transport layer adds the port numbers across which the applications are running. From there, the data packet or the message goes to the network layer. In this layer, the data packet is added with additional information just like the sender's IP address, the receiver's IP address, the routing information, and the switching and subnetting information of the packet. So the sender's address and the receiver's IP address are added on this layer because this is layer 3 and IP address works on layer 3. So the IP address of both the sender and the receiver are added in this layer. Apart from that, everything that is relating to routing and subnetting is added in this layer, and the switching protocol and the types of switching that has to be followed by the packet is also added in this layer. So this network layer adds the IP addresses, that is the sender's and the receiver's IP addresses, along with the routing, switching and subnetting information. So when these informations are added to the packet then goes to the below layer, that is the data link layer. So on the layer 2 or the data link layer, we have the MAC address. So MAC addresses or the layer 2 address works on the data link layer or the layer 2. So data link layer adds the MAC address of the sender as well as the MAC address of the receiver to the data frame. Now one point to remember is that the message or the green box that you are seeing, it is called as a packet in the layer 3 and it is called as a frame in the layer 2. So when this packet comes to the data link layer or the layer 2, it is termed as a frame. So this packet gets transformed to a frame. So this data link layer adds the MAC address of the sender and the receiver to the frame, and then this frame is sent to the physical layer or the layer 1 so that it can be actually transferred in the form of bits or signals from one point to the other point. So when the data comes to the last layer or the physical layer, everything that is in the data frame is converted into binary bits. This binary bit conversion is very useful because it is the only way through which the data can be transferred in the form of signals from one point to the other point, either through a wired channel or through a wireless channel by using signals. So every data inside the data frame is converted into binary digits that is sent over the channel in the form of signals. So this was the sender side. We moved from the application, you typed in hello Muhammad, and that was converted to an ASCII code. After the transformation into ASCII code, a session between you and me was established. When the session was established, the ASCII code was sent to the transport layer so that the transport layer can add the port numbers and TCP or UDP protocols. After that, it comes to the network layer where it was called as a packet. The network layer adds the IP address of the sender and the receiver. In addition, it adds routing, switching, and subnetting information. And when it comes down to data link layer, the layer 2, it adds the MAC address of the sender and the receiver. And when it comes to the physical layer or the last layer, every piece of information is converted into binary digits so that it can be sent as signals over the channel. So this was the left side or the sender side, and now we are going to see how everything happens in the reverse order on the receiver side. So the signals that are in the form of bits, it comes to the receiver side and the physical layer accepts it at the first place. So we are going from the bottom to up on the receiver side. So the physical layer accepts the signals or the bits. These bits are then converted into frames using the reverse process as it was in the senders. So these bits are converted into the frames or the data frames used by the data link layer. The data link layer extracts the MAC addresses and sends the data frame to the network layer. In the network layer, it is called as a packet. In the network layer, the IP addresses are extracted and it is sent to the transport layer. The transport layer sees that okay, it is for port 50, so it sends it to port 50. So once it reaches to the presentation layer, the presentation layer converts that ASCII code or the bits into a format that the Facebook can understand or you can understand. So this is how everything happens from a perspective of a sender and a receiver in all the 7 layers of the OSI model. So each and every individual layer has separate roles. Once the messages go deep into the layers, each layer adds something to the message. So this is how in actuality or in the real world the applications work, from being on the application layer to the physical layer and from the physical layer to the application layer and vice versa. So this is how the communication happens between two communicating nodes in the real world. Let us understand the concept of virtual LANs or VLANs and how they work. A VLAN or virtual LAN is a virtual local area network. So like we saw LANs, virtual LANs are virtual local area networks. So just like we set up a local area network within some definite range, such physical LANs can also be set up using a switch virtually. These LANs are called as virtual LANs. In simple, these are just segments of a bigger LAN. So you have one bigger LAN and you divide that in smaller LANs, and the smaller LANs are known as the VLANs. These virtual LANs will work exactly like the normal LANs, except that they will not be physical in nature. Let's understand more about their virtual nature. Usually for making a LAN, a switch is required. Suppose you are running a tech company that has several departments in it. Since each department needs an individual LAN of its own, you now need to buy several switches so as to keep up with the demand. One solution is to buy many switches and assign different switches for different departments. Thus, every department has an individual switch. The other solution is to buy one switch, just one switch, and divide that switch into different parts. So each part will work as a VLAN and connect different departments together without interfering each other. This way, one switch can be partitioned into different sections that can work independently. In other words, VLANs segregate the nodes that are connected in different LANs by the concept of partitioning or subnetting the main network into many subnetworks. One point to note here is that since the switch partitions the main network or the parent network into independent subnetworks, the nodes within each VLAN can talk to the other nodes in the same VLAN, but not to the nodes of the other VLANs. That means if you have divided a LAN into smaller VLANs, the nodes that belong to the same VLAN can talk to each other, but the nodes that are in different VLANs cannot talk to each other across the different VLANs. The nodes of VLAN A cannot talk to the nodes of VLAN B unless there is a routing functionality provided to them, and that is provided by the router. So now let's understand what this routing functionality means. Since you decided to purchase one switch for all your departments and segregate all the departments into 4 VLANs, let's name them as sales VLAN, marketing VLAN, customer VLAN, and the extra VLAN. The department of sales cannot talk to the department of marketing since they are in different VLANs, or the department of customer care cannot talk to the department of marketing because they are also in the different VLANs. The same is true if anyone from the marketing department wants to talk to the customer care department. He or she cannot do so. The reason is, since you made partitions of VLANs that are independent in nature, they do not have access to send messages across the other VLANs. This access can be given by the principle of routing. So if you add a router to the switch, the VLANs can send messages across their own VLANs. You will understand better what this VLAN routing is when we talk about subnets, subnet masks, and how the different subnets are identified on the network. For now, the point is, if you want different sections of the network to work independently, you need to make VLAN partitions, and if you want those VLANs partition to talk to each other, you need a routing device to that network. Now let us see how many types of VLANs we have according to the services they can provide for the network. So in the environment of VLAN, we have two very important topics, and that is the collision domain and the broadcast domain. So a domain means an area under which something can happen. So an area refers to the domain. So we have the collision area under which the collision can happen, and the broadcast area under which the broadcast can happen. So as per the definition, a collision domain is an area under which the collision of packets can take place while they are using a shared channel. That means such an area in which the collision of data packets can take place when the nodes are using a shared medium or shared channel is known as a collision domain. Now we are going to see in detail what this shared channel means and what is this data packet collision in the next slide. But for now, the collision domain is an area under which the data packet collision can take place when the nodes are using a shared medium or shared channel. Similarly, the broadcast domain is an area in which every node that is inside that area will receive the broadcast message. So if one node broadcasts the message, so every node that comes or falls in that area of broadcast domain will receive the broadcast message. So let's talk in detail about these collision domain and broadcast domain. Now before going further, let's explain what is a collision. So let's say I'm trying to send you a data packet, and at the same time simultaneously you're trying to send me a data packet. If the path is common, then there will be a point at which both of our messages will collide. That is known as a collision. Similarly, in the networking world, when two or more nodes try to send a data packet simultaneously, then a collision happens between those data packets. This usually happens with networks that are using the Ethernet hubs, because as we are told, hubs are not intelligent devices. They do not have their own IQ. They flood the network every time they receive a packet, and when two devices in a half duplex hub channel, half duplex means at one time only one node can send the message, and when the message is received, only after that the next message can be transferred. So in a half duplex hub channel, when two devices send simultaneously, a collision of data packets happen, and the area under which or the link under which the collision can happen is termed as the collision domain. So each port of the hub is in the same collision domain. That means every node that is connected to the hub will be in the same collision domain. So every device that is connected to the hub is in the same collision domain. If the collision happens, it will happen within the range of the network that is connected by the hub. Each port of a switch and router is in a separate collision domain. And by port, we mean that each link that is connecting to the other node. So each link of a switch and router is in a separate collision domain. So that means they can lessen the chances of collision happening by segregating the collision domains at each port. So these are 2 points that you need to remember. First one is each port of the hub is in the same collision domain, and second, each port of a switch and router is in a separate collision domain. So now I guess you might have known what is a collision domain, an area under which collision of data packets can happen when the nodes are using a shared channel like a bus topology or an Ethernet hub channel, etc. Now the second concept is the broadcast domain. So broadcast domain is also a part of the network or the area of the network inside which every device that is inside that range will receive the broadcast message if any node does a broadcast. So for example, if I send a broadcast message, every number of nodes that falls in my range will get that broadcast message. So when any node sends a broadcast message, the message goes to every node that falls within the range of that broadcast domain. Now there is one point in broadcast domain that you need to highly remember, and that is the routers separate the broadcast domains at each of their port. So an area under which the nodes can receive the broadcast messages, those areas are separated by the ports of the routers. So now let's see what are the differences between a collision domain and a broadcast domain, and how you can identify which one is a collision domain and which one is a broadcast domain in the next slide. So a collision domain is an area under which the collision of data packets can happen while they are using a shared channel, and by they he means the nodes. So if the nodes are using an old Ethernet hub half duplex channel or a bus topology, a collision can happen inside the area, and that area is termed as a collision domain. While on the other hand, a broadcast domain is an area of the network under which all the nodes will receive the broadcast message if one node sends a broadcast message. So that is the physical difference. Now the logical difference is that every port of a switch and router is a separate collision domain. Like I told you that switches and routers are intelligent devices. They can separate the collision domains by making use of different ports and VLANs. Thus, every port of a switch and router is a separate collision domain. On the other hand, we have every port of a router is a separate broadcast domain. So like I told you, routers are the boundaries of broadcast domains. The broadcast messages do not go across the boundaries of a router. So every port of a router is a separate broadcast domain. So now I guess you might have got the difference between a collision domain and a broadcast domain. Now the physical difference is very simple, because the area in which the collision can happen is a collision domain, and the area under which the broadcast message can be received is a broadcast. The main difference lies in the logical difference, that is every port of a switch and router is a separate collision. So switch and router, separate collision domain, router, separate broadcast domain. So now let's see how much you got with this activity. Welcome to this section. By now you know what are VLANs or virtual LANs and what are the collision domains and broadcast domain. With the exercise I told you in the previous section, you might have also figured out what are the differences and how to spot where are the collision domains and what are the broadcast domains. Now the next concept is very crucial when it comes to networking, and that is the concept of subnets. Please stay focused over the course of this section, and in this part we are going to discuss the concept of subnets, subnetting, subnet mask and everything. So let's dive in. The very first topic is the subnet. A subnetwork or a subnet is a smaller portion of a large network. In simple terms, when a larger network is broken and divided into smaller individual networks, those smaller networks are known as the subnetworks or the subnets. So like if you have a parent network A that contains 100 nodes, if you divide that parent network into 5 networks that contains 20 nodes each, then those smaller partitions of network will be called as the subnets or the subnetworks. Such partitioning is done so as to reduce the traffic on the main network. When smaller individual networks are formed, every network will handle its own traffic and thus act as individual. This is the biggest advantage of forming such smaller networks or subnetworks. But this division into subnets comes with one problem, and that is once these subnets are formed, once you have divided the parent network into 5 different networks that contains 20 nodes each, these smaller networks or subnetworks, they act as completely individual and independent networks. This is good when the subnets want to work alone and separately, but the problem arises when these subnets have to talk to each other. This means when it comes to collaborative communication, when the subnets wants to work as a team, these subnets cannot work together because of the segmentation by which they were formed. In order to make them talk or message each other, we need to provide them with a way to communicate across each other, and that is the way of routing. The figure shows a parent network A, that is the 100.0.0.0. This is the parent network A. Let's say this network consists of 100 nodes. You have segregated the network A that consists of 100 nodes into 4 subnetworks, that is subnet A with this address, subnet B, subnet C and subnet D. So we have 4 subnets, subnet A, B, C and D, originating from the parent network A. So the subnet A has an address of 100.56.23.0. The subnet B has an address of 100.10.12.0. The subnet C has an address of 100.100.1.0. The subnet D at the last have the address of 100.23.17.0. There is one pattern if you have noted that these subnets have the first part as a parent network address. So if you can see, the parent network has the first part of the IP as the 100, and that is reflected in all of the subnet addresses. And this is correct because this acts as a proof that the network A has given birth, or the subnets has been derived from the parent network A, that was the 100. So since this is the parent and this are the children, they will have the parent network 100 inside them. Everything that is given after the 100 is up to them, but 100 is mandatory because that has been derived by the parent network. But this division or this segmentation is not as simple as drawing a bigger circle for a parent network and drawing smaller circles for the subnetworks. There is a detailed, interesting logic behind the division, and that is with the use of subnet mask. Now before going to the DORA, let us see what the concept behind DHCP is. So in a layman language, this is the diagram how the DHCP works. So on the left hand side we have the client PC. Now this is a PC, it can be anything, your mobile, your laptop, your tablet, your anything, desktop. And on the right hand side we have the DHCP server that assigns the IP to the client. Now behind assigning the IP, there are a lot of stuff going on. So these are represented by these arrows. So first of all, in the first step, the client PC or your computer asks for an IP configuration from the server. It is shown from the client to the DHCP server. Then the server sends a set of IP configuration and asks the client if it is good to use or not. In the third step, if the client likes and is comfortable to work with that IP configuration, it tells the DHCP server that yes, I like this IP address, I want to use that. So it asks the DHCP server, can I use that? So finally the DHCP server says, yes, you can go on and use that IP configuration if it suits you. So this is behind the scenes, where simply the client asks for an IP configuration, the DHCP server provides an IP configuration, the client likes the IP configuration and then asks, can I use that? And then the DHCP server finally says that yes, you can use that if everything is going on with it. This is just a four-way handshake or a four-way communication between the requesting client machine and the DHCP server. So you can remember all of this stuff by learning this DORA word, that is DORA, not that Explorer girl, but the DORA word. So there are four steps that are discovery, offer, request and acknowledgement, all represented by the initial letters of every step. So let us see what these steps are in detail. Alright, so next in the list we have DNS or domain name system. Let's understand how this works. You go to the browser, you type in facebook.com or instagram.com and you hit enter and you land on the Facebook's homepage. It's simple, right? But have you ever wondered how it works? I mean, what are behind the scenes that are involved in converting that facebook.com to that web page? Let us find out today. This magic happens not just with Facebook or Instagram or some random websites, but with every website or web page that is available on the internet. This is due to a service known as a domain name system, a domain name server, or whatever you call it, or simplified as DNS. Some call it domain name server, while some say domain name system. Whatever they call it, the idea functionality of a DNS is to convert the domain names or the names that we type in the address bar to corresponding IP addresses and then vice versa. In simple terms, that means the work of DNS is to convert the domain names into the IP addresses and the IP addresses to their domain names. So it is a mapping from domain names to IPs and back. To understand clearly, first we must understand what is a domain name. So before starting the domain name system topic, we are going to explore what is actually a domain. So a domain name, or simply a domain, is a string of characters and numbers that represents a human readable address on the internet. So whatever you type in the address bar of a browser, that is readable to you, and that is a domain. These human readable addresses are necessary for us to remember because we cannot remember thousands and thousands of IPs to which we have to go to. Simply put, a domain name corresponds to an IP address that is present publicly on the internet. For example, the domain facebook.com, that is the domain name of facebook.com, corresponds to one of the Facebook's server IP. That means when you're typing facebook.com, you are trying to connect to one of the server of the Facebook, and that server might have an IP like 157.240.239.35. You can check the IP of any of the server or web page you are connected to by typing the nslookup command inside the Windows. So it will show you the IP and the DNS properties of those websites or those web servers you are connected to. This means if you type this IP, that is 157.240.239.35, it will take you to the home page of Facebook. When you typed in facebook.com instead of the IP, it took you to the home page. Similarly, it will take you to the home page instead of typing facebook.com just by the IP. There are three different levels of domains, which involves the top level domain name, the host name, fully qualified domain name, and one more. So inside a domain is not just a single piece of text. It is a combination of usually 3 parts or 4 parts, whatever the site likes, separated by dots, and that qualifies as a fully qualified domain name. So let us see what these terms are in detail. Well, let us take an example of www.mypc.com. So this is a domain name or domain. This has 3 parts: www, mypc, and com. The first part is www, that represents the host or the host name. So mypc.com is the domain name. This one is the actual domain name. www is the host name. The last part, that is the .com, is the top level domain name. So mypc.com is a domain name, and inside that mypc.com, .com is a top level domain name. That means it represents the highest level of the domain name. When we club all of these parts, that is www.mypc.com, we are connecting host name along with the top level domain name or the domain name, and thus gives rise to a fully qualified domain name. So always remember, the part before the first dot is always the host name, and the part after the first dot is the domain name. The part after the last dot is always top level domain name, and the whole string when combined is called fully qualified domain name. So now you have gathered more than enough information about the domain name. So let's get back to the DNS or the domain name system. So by now you know how IPs are assigned to a node using the DHCP services in the network. But for sending a message or anything from one node to another node, we must need 4 addresses of the network. These addresses work in conjugation to send a message from one node to the other nodes. So these 4 addresses are a vital need to send messages or even a single ping message from one node to another node in the network. These are the sender's MAC address, the sender's IP address, the receiver's MAC address, and receiver's IP address. So these 4 are the sender's IP and MAC address, and the receiver's IP and MAC address. So if you know the IP and MAC address of your computer, and if you know the IP and MAC address of the destination computer, you can ping from your computer to the destination computer. These addresses, if available, helps in communicating across the other nodes of the network. Now let's take a look at example here. So I'm back at Cisco Packet Tracer, and this is a PC2, that is a device that is connected to the switch, and then we have PC0 connected to the same switch. So now I'm inside the same network and I need to connect to this PC0. Go to desktops and then command prompt, and then inside the command prompt, as I told you that you must know 4 of those addresses so that you can send the messages from one node to another node. Now let's check, do I have 4 of them or not. I'm checking for my addresses. Do I know my addresses? Okay, so my IP is 10.0.0.3, so I know my IP address. And what is my MAC? Let us see, IP config/all. What is this? Okay, space issue. And then where is my MAC address? Okay, and then I have my MAC address, that is 0.0.0.196BE9788. this is the physical address of the link layer address. Okay, so this is my MAC address. You can also see it here in the physical, or if I hover over this here, you will see the MAC address 0.0.0.1.96BE and then 9788. So this is my MAC address. So if I go to this programming, sorry, not desktop, so this is my MAC address. But I do know my MAC address and I do know my IP address. So IP address 10.0.0.3 and the MAC address is this. From this PC2, this is me. I wish to ping PC0, that is the sender. So do I know the sender's IP? Yes, I know it. That is ping 10.0.0.1. I know this because I have set up this environment. Now let me check desktop and then IP config. Okay, 10.0.0.1, this is the same because I have set up, I remembered 10.0.0.1, so I know the destination address, that is 10.0.0.1. so by the time I run this command, that is ping 10.0.0.1, I know three addresses: my IP address, that is 10.0.0.3, my MAC address, that is something with 78, ending with 78, and the destination IP address, that is 10.0.0.1. so if I don't know the MAC address of the destination IP, and I cannot send message without the last piece to the puzzle, that is, I must know all of them, the four of them, to send a message to the destination. But at this moment I know just three things: my IP, my MAC, and the destination IP. Now let's hit enter and see if it works or not. And yes, you see that the messages have been sent, and in turn the messages have been replied to. I was able to send message to the destination, and moreover the destination also replied back to my messages. And how is that possible? I just told you that you need to know four of them, but with only three of them I was able to send messages to that. So how is this happening? Am I saying something wrong? Let's see how this works. Now back to the address resolution protocol. In this case, I knew 3 out of 4 addresses. My IP, my MAC, I know it. Your IP, that means the destination IP, I knew because I set up the environment. For example, let's suppose you want to ping me. Let's assume we both are in a Cisco packet tracer environment, and you want to ping my device. Okay, you know your IP, you know your MAC address, and you know my IP. 3 addresses are enough to send me a ping message. But what about the fourth one? The fourth one was mandatory to provide, and from where it came. Let us see where it came from. It came from this address resolution protocol, or the ARP protocol. The work of this ARP protocol is following. This protocol maps an IP address with a MAC address, just like a DNS, but more specifically it maps a layer 3 address, that is the IP address, to a layer 2 address, that is a MAC address. So by layer 3 address, you can extract a layer 2 address with the following ARP protocol. That means if you know the layer 3 address of a node, which is commonly known as the IP address of a node, the ARP can automatically fetch the corresponding layer 2 address or the MAC address from it. And also, as we learned in the Cisco packet tracer examples in the previous sections, where I showed you how devices works in actual, you saw when we went to the simulation mode, the very first message that was sent was ARP message. ICMP was there, but before that there was another message that was the ARP message. Okay, the main job of an ARP address is to find the corresponding MAC address of the node to which we want to send a message to. So its main job is to find the MAC address or the layer 2 address of a device of which it knows the IP address. Once the ARP message finds the MAC address that is associated to that IP address, it tells the user the MAC information is found, and the user can use that information, send the message to that node. So this is the job of the address resolution protocol, and it is self-explanatory. It resolves the address, and hence it is known as the address resolution protocol. In simple words, this protocol just fetches your MAC address from the IP address. So with the introduction of new section, we are going to start the wireless networking from here. I'll wish you all the best for the next lecture. Thank you. In Wi-Fi, these stations get the internet connectivity by connecting themselves to a central device. This central device keeps every station connected and is commonly known as the access point. If it sounds confusing for now, there is no need to remember this. We will discuss this with a diagram later. For now, just one point you need to remember is that an access point is a point inside a network or a node inside the network to which all the nodes can connect wirelessly. In the diagram, we have two computers, Wi-Fi PC1 and Wi-Fi PC2. Both of these are not using any wires, and hence they are in the wireless network. These computers are connected to the access point via wireless network, and then the access point is then connected to a router via a wired network. The role of a router here is to enable the use of internet so that both the PCs can have internet access. Modern access points have router inbuilt, so they do not need to include an extra device like a router. Like here we have explicitly included the router, but modern access points have the router inbuilt, so they don't need an extra router like in the diagram. Thus, in a nutshell, access points are the devices that helps the nodes to connect together and form a wireless network, and at the same time they also provide internet connectivity to those wireless nodes, which are known as stations. So we discussed in brief about what are access points and how do we connect through them. We also discussed about what are rogue access points and why should we stay away from them. So now let's get back to the main deal, which is how do we connect wirelessly. So I'm saying what is behind the scene that my computer or your computer can connect to the internet through that wireless network. With the wired ones it is easy, you just plug them in and it connects to the router and router to the internet. But what happens wirelessly using an access point, we are going to see that. So let's go over there. Whenever a new node wants to connect to a new wireless network, it undergoes a four-way handshake with the access point. Now you know what is an access point, but you don't know what is a four-way handshake, and we are going to talk about this soon. This four-way handshake is necessary for each node to follow so that they can establish a secure wireless channel between the access point and itself. Before understanding this important procedure, let us understand some short terms related to it. So the first one is a nonce. A nonce is a random number which is generated by the client. By client we mean the nodes that are requested to be connected to the network. In our case, my machine and your machine are going to be the client. So it is a random number which is generated by the clients that are requesting to connect to the access points. So your machine is also generating a code, a random code, and the access point is also generating a random access code. This is used to uniquely identify a node by the access point. The next ones are S-nonce and A-nonce. These are the same as nonce, but these are generated by the client station that makes a request and by the access point that fulfills that request respectively. So S-nonce stands for the station nonce or the node that you're using, that nonce, and A-nonce stands for the access point nonce that you are trying to connect to. So S-nonce and A-nonce are the numbers that are generated by client station and the access point respectively. Then we have S-MAC and A-MAC. Similarly, S-MAC refers to the station MAC address and A-MAC refers to the access point MAC address. So your node does have a MAC address and access point does have a MAC address, and those are corresponding to S-MAC and A-MAC respectively. Now coming to the keys. Now in this four-way handshake, the role of keys are significant. I suggest you jot down somewhere what are these keys and what do they do before going to this four-way handshake, because it's going to be very complicated. So the first key we have is PSK, or the pre-shared key. This is the key which is shared beforehand to both the devices, that is the client and the access point, before the connection actually finalizes. So before you are finally connected to the access point, this key is generated, which is known as a pre-shared key, and it is known to both your client station as well as the access point beforehand. This pre-shared key, as the name suggests, is shared among the station as well as the access point, and it is identical for both of them. PMK, or the pairwise master key. When the PSK, which was generated in the first step, is passed through a key derivation function, that is an algorithm, the resultant is a new key that is known as the pairwise master key. This means that the key generation algorithm that we are using converted the PSK, or pre-shared key, into the pairwise master key. So now we have a new key which is derived from PSK, and that is the PMK. And additionally, the role of PMK, or the pairwise master key, is to calculate the message integrity code MIC for the messages. Now the third key is PTK, pairwise transient key. This key is a combination of PMK, pairwise master key, and A-nonce and S-nonce and S-MAC and A-MAC. So you can see this is a combination of PMK plus A-nonce, that is the nonce of access point, plus S-nonce, that is the nonce of your device or station, plus S-MAC plus A-MAC, MAC of your station, MAC of access point respectively. So when we club all of these together, the algorithm generates the pairwise transient key or PTK. Now before going to the next key, I highly suggest you either take a snapshot of this slide or you just jot down what all those keys are and how they are derived, because it is very useful. The next one is the GTK or the group temporal key. This key is used for encrypting and decrypting the messages that are sent by the client station to the node or from the node to the client station. So that means any message, whether it be unicast, multicast or broadcast, any messages that are going across the two devices, they are encrypted and decrypted using GTK. And the last one is the MIC that I told you. This is message integrity code, and this is used for verifying the integrity of the message. And by integrity of message, we means that the message that was actually sent from the sender is as same as the message that is received by the receiver. That means if the message has not been tampered, the shape and size of the message will be the same as it has been received. The message integrity code is used to confirm that the messages are coming from a legit and desired sender. The first one is the PSK, pre-shared key. The second one is the PMK, pairwise master key, which we get by deriving the PSK through an algorithm. After that, we have PTK, which is derived by combining the PMK, SNONs, ANONs, SMAC and AMAC. The next one is the GTK, group temporal key. This is used for encrypting multicast, unicast or any type of messages in the network. And the last one is the message integrity code, that is for checking the integrity of the messages. So let's assume that the left one is you and the right one is me. So I am the access point and you are the station. In the four-way handshake, we are going to talk, or we are going to send 4 messages among us. So I send the first message because I am the access point. I say I am sending my ANONs, that means I am sending my nonce, which is known as ANONs, to you. You use my nonce to calculate the PTK or pairwise transient key. I have not shown PTK because it will be confusing, but using my nonce, you calculated the PTK. Once you calculate it, you send me a message stating that I am sending my nonce, which is S nonce, to you. So now I get your nonce and I calculate the PTK for me. So by now you know the PTK, I know the PTK. Now I send the third message. It says, hey, are you ready to install the keys? I am ready to install them. If you're ready, we will install them. If you are not ready, I will ask you again in a moment of time. Once we have installed the keys, I will generate a GTK or the group temporal key. So I send the GTK to you, and then you install the GTK, and then you answer me that I have installed the GTKs. Let's use them to encrypt and decrypt our messages from now on. Now this was a very good concept, and now we are using this concept, the four-way handshake concept, and we are going to exploit one weakness that is found by attackers and crackers that are doing researches, and they found one weakness of this four-way handshake that is used to make up connections, and that is known as a crack attack, and we are going to talk about this in the next section. Alright, congratulations on completing this course. Now as per the Udemy's policy, I have to keep this course on 2 hours for it to be a free course, but that doesn't mean everything ends here. Now after finishing this course, what I highly recommend you to do is to check out the full course, that is Mastering the IT Networking full course. Now if you go to this course, you can check out the curriculum of what all the topics we have apart from the free courses, and this course includes 5.5 hours of video lectures. That means every topic that I have clubbed in the free course is here. So you can go through the various sections and check out what are the topics that are being covered here and what are all the topics that were missed in the free course. So I highly recommend you to check out this course, that is the Mastering the IT Networking Fundamentals full course. And thanks again for learning with me. I'll see you again. Thank you.